this video, we're going to cover the bisection method. The bisection method is a technique that we can use to solve equations that take the form f of x equals 0. Here's how it works. Suppose we have the following function and would like to know where this function crosses the x-axis. This kind of equation is actually quite difficult to solve if you're only using algebra. That's where the bisection method comes in. It's a method that we can use to get an approximate solution to f of x equals 0. From the graph, we can see that the solution is going to be between -2 and -1. If we can shrink this interval, we'll get closer and closer to our actual solution, and we do that by following this process. The first step will be to identify the starting interval. In your exam, this will actually be given to you, but for this example, let's assume it's from -2 to -1. Next, we need to identify what the exit condition is. This process can repeat forever unless we give it a reason to stop. So our exit condition is just going to be when we stop the process. There are three main exit conditions that your exam may give you. The first is applied to the width of the interval. For example, we could repeat this process over and over again until the width of the interval is less than or equal to 0.1. The second exit condition is based around the value of the solution itself. For example, we know that we're trying to find where f of x equals 0, but we'll be happy to accept any solution between positive and -0.1. The last exit condition is the simplest. We'll just stop the algorithm after a given number of loops. For example, we could repeat the algorithm 3 times, and the answer is just going to be the result that we found on the third iteration. For this example, we're just going to use the first exit condition. Now we can move on to actually solving the equation. First, we're going to find the midpoint. Our interval is from -2 to -1, so the midpoint is just going to be -1.5. This gives us an x value to test f of x equals 0 with. So we're going to substitute our value of the midpoint into f of x, and we're going to get some result. These are tech-enabled questions because the numbers do get pretty crazy pretty quickly, so feel free to use your CAS. The next step is going to be to shrink the interval. F of m is negative, so m is going to replace the lower bound. If f of m was positive, then m would replace the upper bound instead. Now that we've completed the first iteration, we'll test our exit condition. So we're going to find the width of the interval, which is found by subtracting the lower bound from the upper bound, and this gives us a value of 0.5. This is not less than 0.1, so we're going to move on to the second iteration. So once again, we'll find the midpoint, this time using the new interval. We then test that solution and update our interval accordingly. F of m is negative, hence it's going to become our new lower bound. And again, we'll test our exit condition. 0.25 is still greater than 0.1, so we're going to do a third iteration. So we find and test our new midpoint, but this time f of m is positive, so m will become the new upper bound rather than the new lower bound. We test the exit condition and find that once again, the condition isn't met. One iteration left. Doing one more iteration finally reaches our exit condition. Remember that we're trying to solve f of x equals 0 for x, and the midpoints were giving us values of x to test. So after doing all of these iterations, our answer is just going to be the last midpoint we found, which in this case is M4. The bisection method is often presented as a pseudocode style question, like this one here, which came from the Trial 2023 exam. Pseudocode questions can be tough, so here's a few guidelines to help you approach them. Firstly, look at the name of the function. This question tells us that the algorithm implemented is the bisection method, and you can also find this by reading the name next to the define statement. Just knowing that the algorithm is meant to be the bisection method makes it a lot easier, because before you even read the code, you already know roughly how it's going to work and what the end result should be. Next, we just look at what the question is asking. There are many types of questions that you can ask about an algorithm, and not all of them will actually require you to go through the entire thing top to bottom. In this case, we need to know what value will be returned by the algorithm. This tells us that the return statements are going to be important because that's the only way that an algorithm can return a value. The next thing to do would be to look for the inputs. The inputs are defined at the top of the algorithm, and the specific inputs that we're going to use are defined at the bottom. The inputs are defined in order of the input list. So we'll have f of x equals sin x, a equals 3, b equals 5, and max equals 2. From here, we're just going to go line by line in the algorithm and only stop once we reach our exit condition, which in this case will be when we hit a return statement. So the first line is an if statement. If f of a times f of b is greater than 0, then we're going to run the indented part of the code. Otherwise, we'll skip over that part. In this case, f of a times f of b is less than 0, so we're going to skip that statement. The next statement tells us that the variable I is going to get the value 0. So let's keep track of that. Next, we have a while statement. This statement means that we're just going to continue to loop all that indented code as long as I is less than max. From earlier, we know that max is 2 and that I is 0, so we'll enter the loop. The next line tells us that mid gets a plus b divided by 2. So let's keep track of that as well. Next is another if statement. If f of mid is 0, then we'll return mid. F of mid is not 0, so we'll skip that return statement. The next line is an else if. This line of code can only run if the previous if statement was false, which in this case it was false. F of a times f of mid is less than 0, so our next line of code is going to be the indented statement, which gives b the value of mid. The else statement behaves similarly to the else if statement. It can only run if all the previous statements above it were false. But in this case, the else if was true, so we're going to skip the else statement. The next line tells us that I is going to get a new value, I plus 1. We know from before that I equals 0, so after running this statement, I is going to be 1. We've made it to the end of the loop. This means we have to go back to the top and test that exit condition. I is now 1, and max is still 2. I is less than max, so we're going to jump back into the loop. So we'll calculate the new midpoint using the new values of a and b. Next, we try the if statement. We find that f of mid isn't 0, so we're going to move on to the else if. We see that f of a times f of mid is less than 0, so we're going to update b with the value of mid. Again, we'll skip that else statement because the else if was true. I gets I plus 1, giving us I equals 2. Once again, we made it to the end of the loop. So we'll go back to the top and test that exit condition again. I is now 2, and max hasn't changed, it is still 2. I is no longer less than max, so we'll exit the loop. The next statement after the loop is a return statement. This is what we've been waiting for. We find that the algorithm returns the value of mid, and the last known value of mid was 3.5. So the answer to this question is going to be 3.5. If you found this video helpful and would like to see more, I actually have written versions of these lectures available for free on my website. Just click the link in the description below and it'll take you to my website. Just scroll down a little and click this heading to get access. No opt-in required, free of charge.